Alright, the purpose of this video is to wrap up our discussion of Gaussian data from class on Friday, and also to briefly introduce a new topic of confidence intervals. So you saw that in general, in most analyses, we of course take some subset of a larger population and trust that that data is Gaussian distributed such that our statistics from that subset represent the larger population. And we saw that based on probability, we can use our Gaussian distribution to predict, for example, that a little bit over 2/3 of our data would be expected to fall within one standard deviation range of that mean. Okay, so a couple other things to wrap up. First, we can use the Gaussian distribution to get some idea of the precision of our analyses. And as you saw from the Pogel exercise, that because if we're using a probability set of data such that the area under any given curve is a total of 1, that must mean that if we have very tall sharp peak, it must be very narrow, and if we have a very broad wide peak, it must be short, because the total area under each curve is 1. Okay, and so this generally tells us when we have a nice sharp Gaussian, this is of course much more precise data because all the data points are more closely distributed around the mean, where something like this one would be much poor precision since they're so broadly scattered. Alright, and then finally, one other aspect to discuss is the concept of degrees of freedom. And this is sort of almost a philosophical point. For a whole population, if we have every single member, the total number being n, that would be our degrees of freedom. But of course, we never measure every member of the whole population. We take some subset. All right, and so our degrees of freedom for that subset will always be one less than the number of samples that we measure. Because, for example, say we had wanted 7 total samples, that 7th sample would be determined from the first 6. Or another way of looking at this, if we had a smaller number for argument's sake, say we had 3 values, 9.5, 10.0, and 10.5. Okay, all right, so obviously our average here would be 10.0. Okay, so we could say that these 3 subsamples contribute to this mean statistic. All right, and really we could have any 3 numbers come up to this same average as long as the average worked out that way. So say we said this was 8 and this was 9. All right, and we still wanted the same mean of 10. All right, these two are free to vary, but in order to get this same value of 10, this third value would be restricted to whatever value would average up to 10, which in this case would be 13. Okay, and so if all the other values are free to vary, that last value is always restricted in order to come up with that mean from which these are dependent on. So our degrees of freedom for a sample set is always 1 less than the total number of samples that we measure. Okay. All right, so now moving over to confidence intervals, these are used kind of as the practical application of our theoretical understanding of Gaussians. All right, and for more info on this and some examples, you can see this section in the Harvey E text. All right, so take a moment. You can look over the a couple definitions of confidence intervals here. All right, and so roughly we can think of it, one way we could think of it is if we said mu plus or minus 1 standard deviation, all right, we could say that we have 68.26% confidence that any new measurement would fall within this range. Okay, so that in itself is like a confidence interval. All right, so we can use the probability aspect of the Gaussian to predict these confidence intervals for any data set. All right, and the way that this is calculated is by taking the mean plus or minus S, which is our standard deviation, T, which we'll look at in a moment, divided by the square root of the total number of samples. Okay, so T we can find from this table. All right, and it depends what confidence level we want. So we just looked at an example of 68.26%, one standard deviation, but we could also look at, say, 99.9% confidence, or 95. This is what we probably typically use most often. Okay, and you can see these are dependent on the numbers of degrees of freedom. Okay, so let's look at an example of how our equation applies here. The mean plus or minus t times standard deviation over square root of n. Alright, so the Highway Safety Patrol is testing a new method to measure blood alcohol level. We have these 5 replicate measurements. We have our mean and our standard deviation. Okay, and so our mean, of course, would just be 0.046%. Okay, plus or minus t. Okay, so now our t from our table that we just looked at depends on the degrees of freedom. So we have 5 total samples. The degrees of freedom n minus 1, 5 minus 1 gives us 4. Alright, and we want to calculate the 95% confidence. Okay, so we can look at our column here and find our 95% confidence level at which our degrees of freedom is 4. So our t value would be 2.776. Okay, so we take that times our standard deviation s, 0.00236, that should be enough sig figs, divided by our square root of n, which is our total number of measurements, 5. Okay, and so when we crunch this out, I'll let you work that through and you can find the total value. And so this would be our measurement, and this value would be our 95% confidence interval. Okay, and we can also look at other values as well. We could look at other confidence intervals, or if we had more numbers to the data set, we would use t-values with different numbers of degrees of freedom. Okay, so ultimately what this tells us is that we expect 95% of any data points we measured to be within this range of the mean. Alright, so I'll leave you to the sapling.